Alright, now as promised, here is the video that goes over the practice exam. There are 29 questions. I'm going to go briefly through each question, give some reasons, etc. So let's start with number 1. Here we have a heating curve for a pure substance. Which of the following is true about the substance from point D to E? Alright, so we're looking at this segment. Now notice here it's a flat slope. So what does a flat slope mean? It means phase change. And if you look to the left, that means temperature is constant. Temperature also happens to equal kinetic energy. That's what it measures. So there, it's constant. Kinetic energy is constant. So we could cross off E, A, and B. Now we're looking at the potential energy. See, we're moving from a liquid to gas. We're moving in this direction. So if you remember from the other video, when we go from solid to liquid to gas, that means we're raising the potential energy. Okay, so that means choice D. So raising the potential energy means we're going from more stable to less stable states. Okay, number 2. Particles are arranged in a crystal structure in a sample of... Now if you notice, there's a gas, a liquid, gas, and a solid. So crystal structure kind of indicates some order. So that's choice D, solid. So solids are the most orderly. Number 3. Which two particle diagrams represent mixtures of diatomic elements? So diatomic meaning we're going to see these kind of things. Two of the same kind put together. So that means, if you look at A, that one's a good one. We got some blacks and one white, and then choice C is another one, except in the opposite. So that has to be choice B. Alright, number 4. Which substance can be broken down by chemical means? So something that's chemically broken down can only be a compound. Mixtures are physical. So we're looking for the choice here that has a compound, and the only one that fits is choice A. Everything else is an element. Alright, number 5. Which statement describes a chemical property? Alright, the only one that fits is choice B. Now why is that? Combining, I call that a keyword. Keyword for reaction. And that's typically chemical, not physical. Alright, number 6. An example of physical property. Now it's the opposite. If you look, A and B show react, so that's chemical. Choice C is form a compound, so that's another chemical reaction. Choice D is the only one that fits, form an aqueous solution. So you're just mixing something with water and you make a solution. Well, not always with water, but typically water. Number 7, 10 gram of H2O. Okay, so we got 10 grams as our mass. We're dealing with water, so that means 4.18 joules per gram degrees Celsius is our specific heat capacity C. It starts at 23 degrees Celsius, so that's T1. We're absorbing 209 joules of heat. And we're looking for T2. So you plug everything in. And you get that T2, the final temperature is 28 degrees Celsius. Alright, number 8 contains highest average kinetic energy. This is the same as temperature. So the highest temperature here is choice A. Number 9, converting Kelvin to Celsius. This is also in the reference table. So if our Kelvin here is 20, we solve for degrees Celsius by subtracting 273 on both sides, and you get negative 253 degrees Celsius. Number 10, what is the total amount of heat required to vaporize 1 gram of H2O at 100 degrees Celsius in 1 atmosphere? If you look for H sub V, that's what it is. For water, it's going to be that. Now, number 11, which phase change is exothermic? So, releasing heat or cooling. It's cooling in a way. And that fits with liquid to solid. Choice C. Alright, number 12, another heating curve. During interval AB, which energy change occurs for the particles in this sample? Alright, so here we have another phase change. Flat slope, so that means kinetic energy is constant. C and D are out. So we're focusing on potential energy. This direction, PE increases. Okay, so that's increasing. So only at the phase changes does the potential energy change. And going in this direction on the heating curve, it's increasing. Okay. 13. During which interval is potential energy decreasing and average kinetic energy remaining constant? Alright. If you don't know those parts for potential energy, always focus on the kinetic energy, because that's the same as temperature. So when is temperature constant? That's over here and over here. So B, C, and D, E. Choice C. 14. The graph below represents the uniform heating of sample of a substance starting as solid below its melting point. Okay. So which statement describes what happened during DE over here? I feel like this question's repeated. Choice C. You could look at number 1, it's practically the same thing. Alright, here for number 15 we got another heating curve. What is the melting point? Okay, so know that we're starting at the bottom with solid, here is liquid, and here is a gas. So melting is from solid to liquid, so it's this part right here. And what temperature is that? It's 50 degrees, and if we look down here, the time interval, 2 to 5, it's 3 minutes. So it's choice A. Okay, 16. What is the boiling point of this substance? Okay, know that this substance started out as a solid. So at time 0, it's a solid. From here. And then once it gets to here, notice the constant temperature for a while. So that means we're moving into the liquid phase after that point. So that's melting, not quite boiling. So we still remain at liquid over here until you see another constant temperature. That means it's transitioning into gas. So that here is the boiling point. And what temperature is that? 54 degrees Celsius. Okay. A 36-gram sample of water has an initial temperature of 22 degrees Celsius. After the sample absorbs that, final temperature. Alright. Another Q equals M cat. 1200 joules is our Q. Okay. Mass is 36. initial temperature is 22, C is 4.18, initial temperature is 22, we're solving for T2, and then T2 you get is equal to, you get that T2 is approximately 30 degrees Celsius. Alright, so number 18, heat goes from high to low. So this is heat. So we start with the water being 24 degrees Celsius, and then ice cubes here. So ice cubes typically exist at 0 degrees, so it's going to go from the water being the higher one to the ice cubes. Choice C. It's going to roll into the ice cubes like that. Alright, number 19. Which line segment represents boiling? Alright, here's melting. This one's going to be boiling. It's 22 grams of potassium chloride are completely dissolved in a sample of water in a beaker. The solution is classified as, so we're making a solution. And they typically correspond to homogeneous mixtures, because you're just mixing potassium chloride with water. The potassium chloride breaks down, and regardless of however many samples of water you take, it should be an even amount of potassium chloride in each sample. Alright, which formula represents a mixture? Once again, you look for solutions, and they're typically indicated by right here, the AQ, aqueous. That means you're mixing lithium chloride and probably water to make a solution. Now, number 22. Okay, so it says here you may use more than one term for each substance, for each diagram. So to make it easier, I'm just going to label next to it these terms right here. Okay. Now look at X. We got element A and element B together, stuck together. So that means it's a compound. And compounds happen to be pure substances. Okay, that's it. So letter Y. We got two white circles together, same element. It's not going to be a compound since it's the same element. So this time it's just element, which also happens to be a pure substance. Now Z. We got two white circles representing one element. We got two black circles representing another element. So we got a mixture here of elements. Alright, so here's a ring stand. You've seen this before done in lab, in which we were separating mixtures. So here is a filtration. And this is typically used for heterogeneous mixtures. So that means we're separating small and large particles. Okay, so if you think back to the lab, we were separating sand and salt water. So the sand, being the larger particle, got stuck here. So big gets stuck here in the filter paper, whereas a small one gets filtered through. So salt water, it happens to be NaCl aqueous. So that's a good example to look at. Now looking at these examples, now here I'm going to make a correction of what I said in class. So while we said choice B was the answer, it is actually going to be choice A. Why is it? So while C6H12O6 happens to be a very large molecule, it's glucose from what I've heard, remember, SiO2 here is a solid. If you think back to the lab, we were separating sand and salt water. So sand being the solid was stuck there. So I'm going to add big solid. Okay. So SiO2 is still going to be a pretty big molecule in comparison to NaCl. So it's going to get stuck in there as a solid, stuck in the filter paper, whereas the salt water is going to filter through here. Now number 24, I also said the wrong thing here in class. The laboratory process of distillation does not involve, so distillation, which is same as kind of boiling something. So it particularly uses different boiling points. It must have two different boiling points, the two things you're separating. If you think about it, if you're trying to separate two things with the same boiling point, they're going to both evaporate together. So if they have different boiling points, one boils first, then you're left with the other, so you're able to separate it. So it has to use different boiling points, so it cannot use same boiling point. Alright, number 25. State the direction of heat flow that occurs between the dry ice and the air in the flask. Alright. So heat goes from high to low. Air is high. Dry ice is low. So it goes from air to dry ice. Alright, so here we got a set of data which used for numbers 26 through 28. Alright, so we need to show a numerical setup. That means you don't have to solve, but you just want to see the setup for calculating the change in the thermal energy of the water in the bottle from 7 a.m. to 3 p.m. So this is an MCAT. Because here we notice there's a temperature change. Our mass is 800. Because we're dealing with water, that means our C is 4.18 joules per grams degrees Celsius times our delta T, which is 20.5 degrees Celsius minus 12.5 degrees Celsius. Now that's it. Remember your units. Now if this were physics, you gotta solve it. You gotta do all this work. Equation, substitution with units, answer with units. And so here you'll only require the numerical setup. The last step would be just to calculate it through. Number 27 now, we're looking for a direction of heat transfer. Remember from high to low. So that means if the water in the bottle raised temperature, that means it gained the temperature. That means it must have gained the heat from somewhere else. So it went into the water. And where is it going to go? From surroundings. So the surroundings was actually warmer at first. It went from the surroundings into the water, which is why the water raised its temperature. Now compare the average kinetic energy. Remember that's temperature. So 3 p.m. has higher temperature than 7 a.m. by a difference of 8 degrees Celsius. Number 29. Here we got a diagram that's incomplete showing here the heat equation from liquid water to gas. So notice here, heat is on this side. So this means it's endothermic. That's just a little bit of review. Okay. So we gotta complete the heating curve for this physical change. So what does that mean? That means we gotta show this phase change. So here, we're assuming we're starting from liquid. So we gotta draw this line here to show the phase change. And another line right here to show that it's moving to gas. And what do we call this phase change? We call this evaporation. Okay, now that's it. Hope that was helpful for you guys. Forgive my mistakes in class if you look back on those mixtures questions. And I hope this helps. Good luck, guys.